Our today's guest is Alex Scott from Oxford. Alex is famous of his work in graph theory, in particular on chi-boundedness. He was already our speaker last year, I believe, or 2 years ago. I think it was last year. So yeah, today Alex will tell us about a problem of El-Zahar and Erdős. So please, the floor is yours.
Great, thank you very much. Thank you for the invitation to speak. Yeah, so and particularly in this this joint seminar between the chi-boundedness meeting and the online seminar. Okay, so I'm going to talk today about an old problem of El-Zahar and Erdős that I'm very fond of. I'm going to talk about some joint work with Tung Nguyen and Paul Seymour, both at Princeton. Okay. Right, so there's been lots of interesting things done about chromatic number in the last few years, but there are still lots of sort of mysteries. In particular, it's sort of mysterious how, if you have a graph with large chromatic number, somehow how the chromatic number sits. What's the sort of large scale geometry of the graph? So here's one thing that Erdős and that El-Zahar and Erdős asked about. So two subgraphs of a graph G, so H1 and H2, are anti-complete if they're vertex disjoint and there are no edges between them in your graph. Okay, so you've got two areas of your graph. And the question is, when can we guarantee that your graph G contains a pair of anti-complete subgraphs, both with large chromatic number? So you've got kind of large chromatic number in two different places, no edges between the corresponding subgraphs. Okay, and immediate observation is that it's not always true, because a graph with large chromatic number, it could just be a clique, and of course you can't find a pair of non-neighboring subgraphs in a clique. Okay, so you have to do something. Okay, so let's forbid large cliques. Okay, and this is what El-Zahar and Erdős asked about. So they said if you forbid some clique, so if you forbid a complete subgraph on T vertices, then do you get a pair of anti-complete subgraphs with large chromatic number? So in other words, is there some such function f of T and K? So the first, the T is going to be the size of the complete subgraph, the K is going to be the chromatic number. So if you have chromatic number at least f of T and K, that either you get a complete subgraph on T vertices, or you get a pair of anti-complete subgraphs, both with chromatic number at least K. So they asked, does such a function exist? Actually, they refer to it as these as non-neighboring subgraphs, which is actually a very nice term as well. Anti-complete is now fairly standard, so we ended up using that. Okay, so here's the basic question, which is still very much open. If you have large chromatic number, do you get either a large clique or a pair of anti-complete subgraphs with large chromatic number? Okay, so we haven't solved the El-Zahar Erdős problem, but we have proved a couple of results that we like. So one is the following. So rather than two subgraphs with large chromatic number, you ask for one to have large chromatic number and the other one to have large minimal degree. Okay, so there's a function G, so that if you have chromatic number at least G, then either you contain a complete subgraph on T vertices, or you have a pair of anti-complete subgraphs. One has minimal degree at least K, and the other has chromatic number at least K. Okay, so Erdős El-Zahar asks them both to have chromatic number at least K. We can prove at least you can get one of them with chromatic number at least K, and the other one dense, or minimal degree at least K. Okay, so that's the first result, and then the other result that I'm going to prove, or that we proved. So what if we just ask for two anti-complete subgraphs with large minimum degree? Okay, so you'd hope you could weaken the conditions there. Well, and just ask for maybe if I've got large minimal degree, maybe I can find an anti-complete pair with large minimal degree. So forbidding a complete subgraph is okay, let's type it here. Forbidding a complete subgraph is not enough. G could be a large bipartite graph, complete bipartite graph. So there's no triangle there even, and there's clearly no pair of subgraphs with anti-complete with large minimal degree. Okay, so we're asking, if my minimal degree is large, do I get a pair with large minimal degree anti-complete to each other? Okay, so you have to forbid large complete bipartite subgraphs, and we prove that this is enough. So again, if you have, so chromatic number should be minimal degree here. This is the first time I've used these slides, so I was finishing them this morning, and copy and paste, as always, is terrible because it doesn't change things for you. Okay, there's a function h so that every graph with large minimal degree, not just large chromatic number, large minimal degree contains either a complete bipartite subgraph, KTT, or anti-complete subgraphs with large minimal degree. So either you get a complete bipartite subgraph with T vertices on each side, or anti-complete subgraphs with minimal degree at least K. Okay. Right, so here's what I'm going to do in the rest of the talk. It'll come in 4 pieces. So first I'll talk about the original El-Zahar Erdős problem. So that's chromatic number versus chromatic number, both so anti-complete to each other. Then I'll talk about our first result, that's minimal degree versus chromatic number, anti-complete again. Then I'll talk about min degree versus min degree, which was the second result I mentioned. And at the end, I'll talk a little bit about tournaments and mention a related conjecture on tournaments. Okay, so that's the plan for the rest of the talk. Okay, so let's start by talking about chromatic number versus chromatic number. And let's just start with small cases. So let's start with k equals 2. Okay, so what does that mean? Well, we're looking for either a complete graph on T vertices, or okay, a pair of anti-complete subgraphs with chromatic number at least 2. In other words, well, what's the minimum example? Just 2 edges that are anti-complete to each other. Okay, so a complete graph on T vertices or an induced copy of 2K2. Okay, so this is well known to be true. Wagon showed in the 80s that forbidding, in fact, K copies of K2 gives you chi-boundedness. Okay, and therefore the chromatic number is bounded as a function of T. Okay, and more generally, you can say a lot more. So the Jarfash-Sumner conjecture would tell you that you've got an anti-complete pair with any 2 trees, so any T1 and T2 anti-complete to each other. So just an induced forest with 2 trees. And it's not hard to show in the case of the Jarfash-Sumner conjecture, which is of course very much open, but it does, if it holds for T1 and T2, then it holds the disjoint union of T1 and T2. Okay, but the special case of copies of K2 is much easier. Okay, I should say there are also nice bounds on the actual function you need here. So again, showing that chi-boundedness is true isn't so hard, but getting nice bounds is much harder. Okay, let's move on to k equals 3. So what do we want for k equals 3? We want either a large clique or a pair of subgraphs anti-complete with chromatic number at least 3. Okay, so that means we need a pair of anti-complete odd cycles. Okay, so this case was proved by El-Zahar and Erdős. It was the main results in their paper. I'll just note that a much stronger result was proved by me and Paul Seymour. We showed that if you have a large chromatic number, then either you have a large clique or 2 anti-complete odd holes. Actually, even showing 1 odd hole is not so easy, but we can show 2 anti-complete odd holes and actually 2 cycles of anti-complete cycles of any length modulo whatever you want. So there's a bit of a fairly general result there. Okay, let me talk a little bit about the El-Zahar and Erdős proof. It's a nice argument. So first of all, for the case T equals 3, so the triangle-free case, it's enough to consider a shortest odd cycle. I'll just draw a picture to claim that. So take a shortest odd cycle. and color it, well, alternating coloring. Of course, you need one vertex to have a third color. You look at the neighbors of everything along the cycle. Okay, you can have some pairs of vertices on the cycle with common neighbors, but not too many. Otherwise, you get a shorter odd cycle. So you can't have vertices that are far apart with common neighbors outside. And you check and do a little bit of disambiguation in it, and it gives you a coloring of the cycle and its neighbors. And then everything that is anti-complete to the cycle, so the non-neighbors of the cycle, well, we know we don't have an odd cycle there. Otherwise, we have an anti-complete pair of odd cycles. And so everything outside is bipartite. Okay, so you check, you can get a coloring, and it works. You can show that the chromatic number of the whole thing is less than 8. Okay. What about when t is bigger than 3? So again, there's a nice clean argument here. So let's think about a largest, so clique of maximal size in G. So K is the largest clique. And let's partition the vertices of G according to their neighbors in the clique. Okay, so again, this is the El-Zahar and Erdős proof. So let's just note that, well, no vertex is joined to all of K because we took a largest clique. For each vertex of K, if we think about the vertices that join to everything except for that one vertex, they don't contain an edge. Otherwise, you get a bigger clique. So they have chromatic number 1. For each pair of vertices, well, the vertices joined to all but X and Y don't contain a copy of K3. And so by this first case, chromatic number is at most 8. And then if you take any triple X, Y, Z in your clique, so that forms a triangle, that's an odd cycle. So the vertices that miss that don't contain an odd cycle, so a chromatic number at most 2. Okay, so summing over all the different choices gives you a bound of order t cubed on the chromatic number. Okay, so that works out nicely. Okay, but for K at least 4, so if you want a pair of anti-complete graphs, subgraphs with a chromatic number at least 4, that's open. It's interesting to note that the hard case is where the clique number is small. So, for example, with K equals to 4, so the first open case, cases with t bigger than 3 reduce to the case t equals 3, essentially by the second half of the El-Zahar and Erdős argument, and they noted this. So actually for K equals 4, the only open case, and all the problem is in, if you have a triangle-free graph with a large chromatic number, then does it contain 2 anti-complete subgraphs with chromatic number 4? Okay, so that's what you need to do for the K equals 4 case. Okay, but that appears to be difficult and interesting. Okay, so that's everything I'm going to say about the El-Zahar and Erdős argument and problem. Let's move on to our first result. So minimal degree versus chromatic number. So here's the goal. You want to show there's a function g so that if you have chromatic number at least g, either you contain a large complete subgraph or you have a pair of anti-complete subgraphs. So yeah, a pair of anti-complete subgraphs, one of which has large chromatic number, one of which has large minimal degree. Okay, so let me sketch the argument for that. Okay, so first of all, it's going to be useful to find parts of the graph where they're kind of reasonably dense. The vertices outside aren't too dense into the subgraph that we've got. So we're looking for a subgraph where it's got large minimal degree, but vertices outside don't see too much of it. Okay, so the tool here is going to be this notion of a p-rock. So a rock, p is the parameter. So it's a set A where the number of edges is at least p times the number of vertices. So the number of edges in the subgraph induced by A is at least p times the number of vertices. And we want to choose a good p-rock, or a good rock. So we have a minimality condition. So we take as few vertices as possible in our set. And then if we still have a choice, we take an example with as many edges as possible. So first we minimize the number of vertices, then we maximize the number of edges. Okay. So let's just note that if you have lots of edges, if you have at least p times as many edges as vertices, then you certainly do contain a p rock. So because the first bullet can be achieved, and then the second and third are just by minimality. And also by minimality, you can check that the chromatic number of a p rock is bounded. I don't care too much about the precise bound, just that it's bounded, in this case, by at most 2p plus 1. Okay, so that's again the definition of a rock. And I want to claim that, okay, so if I have a p rock, I mean, that's pretty good for a set with large minimal degree. Let's just check that vertices outside aren't too dense to it. So I claim that if I have a p rock, then every vertex outside has at most 2p plus 1 neighbors inside. Okay, and the proof's very simple. So first of all, you look at the subgraph induced by your p rock, and you note it has well, it has at least one vertex with a degree at most 2p. Otherwise, we can just delete a vertex and get a smaller p rock, so that breaks the first of the two minimality conditions. So, okay, so it has at least one vertex of minimal degree. And now if we have a vertex outside with lots of neighbors in A, we can get a better p rock. So we can get the same number of vertices and more edges by kicking out the vertex with minimal degree and putting in the vertex with lots of neighbors in A. So that just makes it a little bit denser. Okay, so by the second minimality condition or maximality condition, no vertex outside has more than has 2p plus 2 neighbors. Good. Okay, so p rocks have this nice property that they have large minimal degree, so large average degree, and vertices outside aren't too dense coming in. Okay. Now, that kind of sounds like a nice picture. Just a little caveat. 2p plus 1 neighbors, so a p rock doesn't need to be terribly big. So you could have a vertex outside that sees almost all of the p rock. If your p rock has lots and lots of vertices, much more than p, then vertices outside only see a small fraction of it. Okay, so we've just got that there's at least some absolute bound on how many vertices in a p rock a vertex outside can see. So this is going to turn up a bit later where we think about how big the rocks are. And if you have a very big rock, then vertices outside don't see too much. If you have a small rock, you maybe have to be a little bit more careful. So vertices outside can easily dominate it. Okay, so now back to the proof. So we'll argue by induction on T, on the size of a complete subgraph we're after. And let's pick a couple of constants, P and Q. So P is going to be 32K, so it's going to be some reasonable constant times the chromatic number we're after, and then Q is going to be something a bit bigger than P. Okay, and let's suppose chromatic number is large. Okay, so I'm not going to worry, again, I'm not going to worry too much about explicit constants. I'm just going to mention that the constants are there. The point is I'm just going to try to give you the flavor of the proof. So here's the thought. Let's take our P rock, A, and let's look at the edges. And let's try and divide up the edges into lots of matchings. Okay, so what we're looking to do is we're going to find our dense subgraph inside the P rock, and then the large chromatic subgraph is going to be outside the P rock. And we're going to have to think about how vertices outside see edges inside. And in particular, we're trying to find a large chromatic piece of the graph outside the P rock, outside A, that misses a piece of A with large average degree. So this is what we're trying to do. Okay, so let's do a bit of work to decompose A. So we'll take the edges, we'll divide it into lots of matchings, lots of edge disjoint matchings of size Q. So we'll just greedily take them out until there are none left. And then what's left? Well, if there's no matching of size Q, well, just take the largest matching you can, and the vertices of the edges in that matching will hit all the remaining edges. Okay, so we can partition the edges of A into some collection of matchings of our chosen size Q. Remember, Q is just going to be some large constant times the minimal degree that we're after. and let's just write M star for the remaining edges of F. So we've got lots of matchings, and then a sort of leftover set of edges with a small hitting set. So there's a small set, which I'm calling B, of most 2Q vertices that hit all the edges that aren't in the matchings. Okay. Right, so first observation, we can assume that A, the site, this is our rock, is not too big. So it is big, I mean, it's not too small. Okay, why? Well, we can apply induction, and each vertex in A, if we look at its neighbors, so the neighbors don't contain a complete graph on T-1 vertices, and so by induction, chromatic number of the neighbors is not too large. Okay, so it's at most F of, I've got, another typo, F of T-1 and K, not K-1 and T. So by induction, the chromatic number of the neighbors is not too large. Okay, so if we take A and all the neighbors of A, if A is small, then altogether the chromatic number is not too large. So the non-neighbors of A have large chromatic number. So we can just take suitable piece of A, any piece we want, anything with large minimal degree, and the non-neighbors of A have large chromatic number, and we found the pair of subgraphs that we're after. Okay, so we can assume that A is large and 8Q squared is large enough. Okay, what about B? So B is this hitting set. It's going to be convenient if B has no neighbors outside A. So let's just delete all the vertices that are adjacent to B that lie outside A. And again, B has bounded size, 2Q. So the vertices that are outside A but have a neighbor in B, they have small chromatic number by induction. Let's just remove them all. Let's C be the remaining vertices outside A. So we just cleaned it up a bit. We've got our set A, we've got B, and the rest of A, and then we've got C outside with no edges to B. And C still has very large chromatic number. Okay, so here's what we're going to, this is going to be the crucial lemma. We're going to divide up A, or A minus B rather, into a number of sets with the following property. So it's going to be 4p plus 2 sets, so that if I take any 2p plus 1 of them and take the union of them and then throw in B as well, I get a subgraph with large average degree. Okay, so I'm going to have 4p plus 2 sets. If I take half the sets, whichever half of the sets I take, and throw in B as well, I get a subgraph with large average degree. And in particular, I get a subgraph that's going to contain something with a large minimal degree. Okay, so it's good for my dense case. So if I can find in C, outside A, some subgraph with large chromatic number and no edges to some collection of 2p plus 1 sets from my partition, then I'm going to be in good shape. Okay, so this is going to be the target. Okay, so we need the following claim. So I can partition A minus B into 4p plus 2 sets, so that given any 2p plus 1, take their union together with B, I get lots of edges. Okay, right, let me just sketch the proof very quickly. So it's just going to be a fairly straightforward probabilistic argument. So just take a random partition, to uniformly random among all partitions, and we'll show that this works with positive probability. So we have to show it works for each S, and there are 4p plus 2 choose, that should be 2p plus 1 choices for S, and we'll show that each is good with very small failure probability. Okay, and it's going to be small enough so that a union bound will then work. Okay, so I'll just sketch this very quickly. So let's fix a choice of S, and there's going to be 2 cases depending on how the edges in A are distributed. So firstly, if half of them are incident with B, then, okay, so let's just think about the edges between B and A minus B. And, okay, we're partitioning into 4p plus 2 sets and taking 2p plus 1 of them. So each vertex is in A sub S with probability half. Okay, so each vertex independently belongs to AS with probability half. Remember, B is not being partitioned, B is just sitting there, so it's only one end of each edge that we're arguing about. And also, each vertex, how many edges of interest does it belong to? Well, only the ones to B, and there's at most 2Q, there's at most the size of B of those. So it's just a binomial, and a kind of straightforward Chernoff bound shows that with very small failure probability, at least a quarter of those edges, so you expect to get a half, you get each edge with probability half, and just a straightforward Chernoff argument shows that with very small failure probability, you get at least a quarter of them. Okay, so, okay, what's the other case? So half the edges of GA lie inside A minus B. So now we've got a graph on A minus B. Let's look at it. So each individual edge, well, the probability it lies inside AS is a quarter, because, I mean, if you think about an edge XY, X is in your AS with probability half, Y is in AS with probability half, so probability that both ends are in is a quarter. Okay, but it's not quite so simple, but here's where our matchings are useful. Okay, so the matchings contain all the edges that lie inside A minus B. And now if we look at just one matching at a time, so the probability that probability we get, well, we expect to have a quarter. So by a Chernoff bound, the probability that MI will have less than, there should be an eighth rather than a quarter of its edges. Expect to have a quarter, the probability you have an eighth is very small. Again, it's just a binomial. You're very unlikely not to get an eighth of your edges inside A sub S. And so I apologize for the typos here. Yeah, you're very unlikely to have less than an eighth of your edges in AS. Okay, so let's say a matching is good if it has at least an eighth of the edges in AS, and bad if it has less than an eighth. An individual matching is very unlikely to be bad, so the expected number of bad matchings is very small. And so by Markov's inequality, it's very unlikely that you get more than half the matchings being bad. Okay, so it's sort of straightforward probabilistic argument. You have to sort of do a little dance and it works. Okay, so put those two together and add up the numbers and you get what we wanted. Let me just rewind. We get a partition so that any 4p plus 2 sets, so that any 2p plus 1 of them, the union of those together with B, is reasonably dense, has lots of edges, large average degree. Okay. Good. So let me just say again where we've got to. So we've got a P rock A, and we partitioned that into a set B. That was our hitting set for the leftover edges, and then 4p plus 2 other sets, and then we have a set C. And they have the properties that if I take any 2p plus 1 of the AI together with B, I get a subgraph with large average degree. There are no edges between B and C, because we deleted all the neighbors of B outside A. And then C has a large chromatic number. Okay, so this is what we did all the work to get, and now the rest of the argument goes nicely. So each vertex of C, well, by the lemma about P rocks, we know that it has at most 2p plus 1 neighbors in A, as A is a P rock. Okay, so it has neighbors in at most 2p plus 1 of the sets AI. So in particular, there's some set of 2p plus 1 AIs that it misses. So there's some S of size 2p plus 1 so that V has no neighbors in AS or in B. Okay, so let's write CS for the vertices that have that property for S. And the sets CS partition C. C has very large chromatic number. So one of the sets, CS, must induce a subgraph with large chromatic number. Okay, so CS and AS union B. So CS has no neighbors in AS union B. So CS is a graph with large chromatic number, and AS union B is our graph. Okay, that has large average degree, and of course you can drop to a subgraph with large minimal degree. Good. So that's proof of the first result. Okay, so let me pause for a second. Right, so we've seen that you can get large chromatic number gives you either a large clique or a pair of subgraphs, one of which has large minimal degree, one of which has large chromatic number. And now, and the same typo, I'm sorry, it's going to come up again. So this should be large minimal degree rather than large chromatic number. There's a function h. So now we're going to go for a pair of subgraphs with large minimal degree and anti-complete. And the assumption is going to be that you have large minimal degree. So there's a function h so that every graph with minimal degree at least h contains either a complete bipartite subgraph, KTT, or a pair of anti-complete subgraphs with minimal degree at least k. Okay, so let me again sketch the argument for this. So in fact, what I'll do is I'll sketch half the argument, then I'll wave my hands for the second half. Okay, so again, we're going to use rocks, but this time we're going to use a bunch of them. So the problem somehow is that you might have very small rocks. So what you'd like is a nice big rock, and then you'd like to be able to do the same sort of thing as we did in the previous proof. But you have to deal with the problem that actually may only have very small ones. Okay, so let's suppose first that there are lots of small rocks, in fact, lots of small disjoint rocks. So say we can pick just a sequence of small rocks. So 2T rocks of size at most some of any constant you want, let's say S. Okay, so let's R be the union of these rocks. Let W be the vertices that have neighbors in, well, at least half of the rocks. Okay, and at least T of the rocks. Okay, so here's the nice thing, W is not too big. So remember, we're after a complete bipartite graph with T vertices on each side. So if you have neighbors in T rocks, actually the union of all these rocks is not very big. And so you can quickly see there can't be too many vertices with at least T neighbors in the union. Okay, so here's one way of writing the bound. You can choose T out of the 2T rocks. In each of them, you have to choose a neighbor. And you can't make the same set of choices T times, otherwise you get a KTT. Okay, so the total number of vertices in W is just some constant. Okay, so actually we can just delete W without reducing the average degree by too much. So if you delete one vertex, it reduces the average degree by the most constant. Okay, so now we've got our 2T rocks, and nobody outside the rocks has neighbors in more than T of them. Okay, so right. So for each I, let's write Zi for the vertices with no neighbors in the rock Ri. Okay, so actually typically vertices outside will belong to lots of different Zi's. Okay, but the key thing is that Zi and Ri are anti-complete. So again, Ri is going to be our candidate for one of our large minimal degree subgraphs, and Zi is going to be where we look for the other large minimal degree subgraph. Okay, and they're anti-complete to each other, so we're kind of in good shape there. Okay, if I think about any edge that sits outside the union of our rocks, then both ends of the edge have neighbors in at most T-1 of our rocks, and so there's some rock in which neither of them have any neighbors. So there's some J such that neither X nor Y have a neighbor in Z sub J. Okay, right, so every edge outside R belongs to at least one of the Zs. Okay, and since outside R we have large average degree, R's got bounded size, it follows that one of the Zs must have large average degree, and therefore the pair RJ, ZJ will do, I mean, after dropping down to subgraphs with large minimal degree. Okay, so that does the case where we have lots of little rocks. What about when we don't? Well, it tells us we don't have too many disjoint small rocks, so just greedily take as many small rocks as you can, and then just delete them all. delete all the vertices in those rocks. And then what's left, you've got no small rocks. So now all the rocks are big. And essentially, you follow a very similar strategy to the other proof. So I'm not going to go through the proof. I'll just say it's a similar strategy. There are a few differences because we're getting rid of KCT rather than KT, and we're dealing with minimal degree rather than chromatic number. But the strategy is very similar. So similar sort of argument. Good. So that's how the second argument, second theorem goes. So that leaves me with one more thing that I want to talk about, which is coloring tournaments. So tournament coloring is it's interesting. So it's a bit different from graph coloring, but a bit similar at the same time. So it's there's lots of interesting questions, and we know about lots of questions. We've got lots of things we'd like to know, and most of them we don't know the answer to. So there's lots of interesting questions. So first of all, what is the chromatic number? So your notion of a kind of color class, rather than, I mean, for graphs you're looking at stable set. A good analogy for that is a transitive tournament. So that's sort of the nicest possible tournament in some sense. So the chromatic number of a tournament is the smallest k, so that you can cut up the tournament into k pieces, each of which is a transitive subtournament. Okay, right. So here's a conjecture, and here's a conjecture that it's going to turn out to be stronger than the El-Zahar and Erdős property. So conjecture is that for every k, if you have a very large chromatic number, then there's some pair of subtournaments, disjoint subtournaments, so that they both have large chromatic number, they both have chromatic number at least k, and the first one is complete to the second one, which means all the edges between A and B go from A to B. Okay, so that's the conjecture. Let me relate that first to the Erdős, to the El-Zahar and Erdős question. So there's a natural way and very well known way to connect graphs to tournaments. So given a graph, think about some ordering on the vertex set. So I've got the vertices are labeled V1 up to Vn, and given the graph together with the order on the vertices, then you can define a tournament with G as its back edge graph, and it's exactly what you'd think. So edges go upwards from I to J, from Vi to Vj, where I is less than J, unless they're in G, in which case they go back down again from Vj to Vi. So G just encodes which edges go from right to left. So the default direction is left to right unless you're in G and you go from right to left. So if G is just a stable set, you just get a transitive tournament going up. If G is a clique, you get a transitive tournament going down. Okay, so if you have a stable set in G, then you get, as I said, you get a transitive subtournament in T, and that tells you that the chromatic number of the tournament, so if T comes from G, the chromatic number of the tournament is at most the chromatic number of G. Okay, just take a coloring of G, and that transfers immediately to a coloring of T. Okay, converse doesn't hold. For instance, G could be a clique, in which case it's got a huge chromatic number, but the tournament has chromatic number 1. But it turns out that if G doesn't contain a large complete subgraph, then chromatic number of T is, that should be chromatic number of G over T, not K, and that's just chromatic rather than chromatic. So chromatic number for the graph and the chromatic number of tournament are tied if you bound the clique number of G. Okay, and that's an easy argument from Dilworth's theorem or exercise. Okay, so we're thinking about graphs with bounded clique number, and that tells us that chromatic number of the tournament and the chromatic number of the graph lie within a constant factor of each other. So when we try, this is going to allow us to do a bit of translation backwards and forwards. Okay, so I claim that conjecture implies a positive answer to the problem of El-Zahar and Erdős. That should be. So here's the proof. So given a G with no complete subgraph on T vertices and vertices V1 up to Vn. So I'm specifying the ordering. We translate it across to get a tournament T. And by the conjecture, we can find subtournaments A and B so that they both have large chromatic number and A is complete to B. So that's our setup. Now, that's great in the tournament. It's not so good for the graph at the moment, because when we go back to the graph world, A and B could be interleaved in some complicated way. Okay, so let's just clean it up a bit. We'll shrink to a subset of A and a subset of B so that one comes before the other. Okay, and that's straightforward to do. So you take the smallest I, so you just look at the restriction of A and B to initial segments of your vertices, V1 up to VI. And you carry through until the first point where one of them has large chromatic number, say half the chromatic number that you started with. Okay, so either A or B, when restricted to V1 up to VI, has chromatic number reasonably large. Okay, and that means, well, the other one, if you restrict it to the rest of the vertices, so VI plus 1 up to Vn, also has chromatic number large. So you've got A prime and B prime. They now, one comes before the other, they both have large chromatic number, and A prime is complete to B prime. So there's two possibilities. A prime comes before B prime, or A prime comes after B prime. And let's just see what those two give. So if A prime comes before B prime, then all the edges go up. So when we translate back to the graph again, they give us non-edges. They're not in the back edge graph because they're upwards edges. Okay, so we get anti-complete pair, whatever came from A prime, whatever came from B prime, and by our observation before, we keep large chromatic number. Okay, the other possibility is A prime comes after B prime, and now they're completely joined when we translate back to the graph case. Okay, but now we're done by induction because we're bounding the clique number, and so we drop inside these subgraphs. Okay, so this tournament conjecture implies the positive answer to the El-Zahar and Erdős problem. Okay, so I should say the conjecture does seem very strong, but we haven't been able to disprove it. So it might be true. Here are two pieces, two small pieces of positive evidence. Okay, so we can do the first case in some sense. So for every K, if you've got large chromatic number, you get a cyclic triple, so just 3 vertices with the edges going round, complete to a subtournament with large chromatic number. So we can push the chromatic number up on one side, and then just to cyclic triple on the other. So that's chromatic number 2. Okay. The other thing we can do is, if you replace the assumption of large chromatic number with large domination number, so domination number is the smallest. You could say either out domination number or in domination number here. It doesn't matter. You just make a decision. Let's say out domination number. So that's the number of vertices you need so that they're out neighborhoods. The union of those cover the rest of the tournament. Every tournament with sufficiently large domination number contains disjoint subtournaments A and B, so that they both have large chromatic number and A is complete to B. So the conjecture is true if we have a tournament with large domination number. Okay, and there's an interesting interplay and comparison between large chromatic number and large domination number. There's sort of two interesting, they interact in interesting ways. Okay, okay, so I've gone slightly faster than I expected, but let me just finish. So here's just a conjecture again. Yeah, we'd be very interested to know if this is true. It'd be very nice if it were. Okay, thank you very much. That's it.